The first speaker is Professor Alfred Vaino Eho. Professor Alfred Vaino Eho is a Canadian computer science scientist, best known for his work on algorithms and data structures, programming languages, compilers, and related algorithms, and his textbooks on the foundations of computer science. His innovative research in formal languages and compiler theory led to key algorithms for modern compilers and string pattern matching tools. He has a Bachelor of Applied Science degree in engineering physics from the University of Toronto and a PhD in electrical engineering computer science from Princeton University. He is currently the Lawrence Guzman Professor of Computer Science at Columbia University. In 2003, Professor Eho has received the IEEE von Neumann Medal for contributions to the foundations of computer science and to the fields of algorithms and software tools. He is a member of the U.S. National Academy of Engineering, the American Academy of Arts and Sciences, and the Royal Society of Canada. His book co-authors include John Hopcroft and Jeffrey Ullman. So please, Professor Eho.
Thank you very much for that kind introduction. I'd like to begin by saying how humbled and deeply honored I am that we're being recognized for our work in theoretical computer science and our contributions to computer science education through the NEC Foundation C&C Prize. It's truly a great honor. I noticed one of the things that was on the slide was, what advice do we have for young computer scientists? And I get this question a lot from my students of where should I go and work? And my response or answer to them is always the same. Go and work where you can work with the best people in the field. And this has been both an honor and a privilege for me throughout my entire career, that when I arrived at Princeton University, I met Jeff Ullman in the registration line, and John Hopcroft became my thesis advisor. So I started off very well by being able to work with the best people in the field. After graduating from Princeton, I joined Bell Telephone Laboratories in the United States. I joined the Computing Science Research Center. This was the research center that created, amongst other things, the Unix operating system, the C and C++ programming languages, and it provided me another opportunity to work with some of the very best scientists, mathematicians, and engineers in the world. And it greatly influenced my career and gave me an opportunity to explore problems that I would not have otherwise encountered. So what I'd like to do in this talk is mention some of my adventures in pursuing the field of algorithms and software. This was propelled initially by the work that John and Jeff and I did in research in algorithms, and then we decided to codify some of the field through our books. And we were quite gratified, maybe surprised, that the books were widely adopted by universities around the world and used in the first algorithms courses. And many people meet me and say, "Oh, I used your book." And this may be 10 or 20 years after I'd written the book and forgotten what I had written in it. But on the other hand, another thing that I say to young scientists is it's important to do good work, but it's also important to teach others how to use your work, because then you start developing a reputation and a cohort of people who can take your ideas and use them for the betterment of science, engineering, and hopefully humanity. So this is the only advice I have for young people. Work with the best people that you can, because you learn so much from them. So what I'd like to do is talk about the evolution of algorithms. Many people claim that the internet is the invention that has had the most impact on humanity, and there may be some element of truth in this. Over half the people on the planet are connected to the internet, and I recently noticed that in Japan there are over 100 million people on the internet. This is well over half the population of Japan. In 34 years, this is from the time that TCP/IP was adopted as the bearer service of the internet, this invention has had profound impact on humanity all over the world. Cell phones may be having an even more profound impact because all the young people that I know use them. But why has the internet become so popular? Well, the short answer to this is there are all sorts of interesting applications on the internet, all of them enabled by computers and communication. But what I think is underappreciated is that every one of these applications depends on software. And I'm trying to get more respect for software in the world, and this sometimes is an uphill journey. We might begin by asking, how much software does the world depend on today? About 12 years ago, I wrote a paper for Science magazine entitled Software and the Future of Programming Languages. And in the beginning of the paper, I asked 3 questions. How many unique software systems are in use in the world? How much does it cost to produce a finished, documented, tested line of software? And what's the defect density in this software base? Short answer to this question is that there's an incredibly large amount of software in use around the world, and the world depends on today. And I saw this slide on the internet recently, looking at the size of some popular software code bases. And they're measured in the tens of millions to hundreds of millions of source lines of code. I might ask the NEC executives, how many lines of software are in your product line? I asked this question repeatedly at Bell Labs and AT&T when I was there. And slowly I got the begrudging acceptance by the senior management of AT&T saying, yes, software is very important and we should pay attention to it. Because if you don't pay attention to it, you'll be put out of business by it, as we've seen with a lot of companies around the world, and seeing what companies like Google and Amazon are doing to established businesses. So be aware of the potency of software. There's also a movement, because of the importance of software, to put coding as part of the educational experience in elementary schools and high schools. And I don't think coding per se is the right way to think about software and algorithms. And here is my view of what should be done. You have a problem domain, and for that problem domain, you'd like to come up with an abstraction, a mathematical abstraction for the problems in your domain, and you'd like the abstraction to be such that then problems can be solved using algorithms and software systems to solve problems in that domain. And one of my favorite examples of this is we hear a lot about quantum computing these days, but fortunately the physicists developed a very useful abstraction for thinking about quantum computing in the first 20 years of the 20th century called quantum mechanics. And if we look at the software systems that are being developed for quantum computing today, they're all based on quantum mechanics as a computational abstraction. And I'll say more about this shortly. Well, just to again underscore the point of why software, well, because every software system implements a collection of algorithms. So algorithms are the starting point for thinking about software. But you need more than just algorithms per se. To make algorithms alive, to make them useful, you need programming languages and compilers. But let's first define what we mean by the term algorithm. And so I went back to one of our early books, and it says in there, this is what an algorithm is. It's a finite sequence of instructions, each one of which has a clear meaning and can be performed with a finite amount of effort in a finite length of time. Think of an algorithm as a recipe for a computation. And another statement that we made in an even earlier book is that algorithms are at the very heart of computer science. Today, I would say algorithms are at the very heart of the internet era. But you also need some kind of engine or machine on which to execute an algorithm. And I just picked 4 of the many models of computation that have been suggested for executing algorithms. One of the earliest is just having a person with a pencil and paper, like in Euclid's day or somewhat after that. In our Design and Analysis of Algorithms book, we created a model or used a model called the random access machine, which is sort of an abstraction of a von Neumann computer. And if you deal with functional programming languages, Alonzo Church's The Lambda Calculus is considered one of the greatest models of computation ever invented. And if you're more engineering oriented, you can think of circuits with Boolean gates. These are the fabric with which computers are made today. In our 74 book, one of the things we did, which I thought helped the field enormously, was saying, rather than trying to find a solution for an individual problem, let's look at algorithm design techniques that can be used for whole classes of problems. So this amplifies your ability to be able to create efficient techniques for solving problems. And some of the techniques that we advocated were recursion, divide and conquer. The fast Fourier transform is just an instance of divide and conquer. Dynamic programming, like the diff program on Unix, is just an example of dynamic programming. You may have heard of the Viterbi algorithm. That's just another example of dynamic programming. But having a name for a general class of techniques immediately facilitates communication, because you can say, have you tried divide and conquer? Have you tried dynamic programming? And immediately you are stimulated to think about how that approach could be applied to the problem domain. And the reason I include this is that my colleague Jeanette Wing recently, she's our new head of the Data Science Institute at Columbia University, she gave a talk to the entire university on data science. And after her talk, a history professor from Columbia College came and said, algorithms are so important. I'm going to teach one algorithm to my history students in the first year at Columbia. What algorithm do you recommend they teach? So she asked some of us in the computer science department, what would we recommend? And I immediately said, why don't we pick this very honorable, very old, ancient, but beautiful algorithm called Euclid's algorithm for finding the greatest common divisor of 2 integers. And here's a rendition of Euclid's algorithm written in a modern recursive form. What is nice about this is that this same algorithm is still in use today. How many algorithms do you know that are 2,500 years old that are still in use today. Another important aspect of an algorithm is the amount of time it takes to run that algorithm on a computer, and the time is usually measured as a worst-case running time on inputs of size n. And here are some examples of time complexities for common tasks like sorting n numbers or multiplying two matrices or determining whether a Boolean expression has a satisfiable truth assignment. And I'll say a little more about the impact of looking at the computational complexity of an algorithm in today's world. As soon as I got to Bell Labs, I was interested in finding patterns in strings. There was a program that Ken Thompson had implemented on Unix called grep. It was one of the most widely used algorithms or tools for searching for just simple patterns in text files. And on one occasion, when we were writing the Design and Analysis of Computer Algorithms book, I gave a talk on algorithm design techniques. A member of the Bell Labs Technical Information Libraries came to me. She had written a bibliographic search program that would search a tape of current technical papers and reports that came from the US government for looking for various keywords and phrases that a bibliographer might be interested in. And she mentioned to me that the night before, some gung-ho bibliographer had specified a search with over 100 keywords and phrases. And the program had a $600 limit on how much time could be spent on a search. And she said, with your fancy algorithm design techniques, can you help? And I said, well, have you considered building an automaton that will look for these keywords in parallel? So you just read a bufferful from the tape, search for all of the 100 keywords at the same time, and then proceed. So a few weeks later, she came to my office and said, remember that run that used to cost $600? Now it costs $25. This is the cost of reading the tape, not of how much time it took to find the patterns. I mentioned this to my boss, and he immediately said, keep working on those algorithms. They're going to be important someday. So I got a lot of encouragement to look at algorithms. And then I was also interested in doing more general pattern recognition and created a program called egrep. I implemented the so-called Aho-Corsic algorithm in fgrep and egrep. These two programs are on Linux, and they're still amongst the most popular programs for searching for patterns in text files. Now, I mentioned that in addition to an algorithm, you need to implement it in software, and you do this through some programming language. Today, there are thousands and thousands of programming languages in the world. I'd like to talk about one specific language that I'm particularly fond of on this list, a scripting language that got to be known as awk. I'm the A in awk, W is Peter Weinberger, and K is Brian Kernighan of Kernighan and Ritchie fame. Each of us wanted to have a little language for doing routine data processing tasks, and we wanted the language to be simple, easy to use, and you didn't want to write big programs. So I mentioned a computational model, and our computational model for awk is that the program is just a sequence of pattern action statements. The patterns you specify, and you look for some kind of interesting sequence in the input, and if you find it, you execute the action associated with this. It's a stimulus response kind of language. It's a very natural human way of doing things. The model of computation was we search each line of every input file for every pattern in the awk program, and if we find a match for the pattern, then we execute the associated action. So if you have a simple file that consists of names and telephone numbers, and if you say the first field matches Hashimoto, and you say print the second field, here's a way of finding Hashimoto's telephone number. Now you're expert awk programs. That will work on your Linux system. Here were some of the, there was a interesting article in the Lua webpage about can we create a programming language that could compete with awk with one-liners. And I found this last awk program that creates a program to print all unique input lines in a file. It's just an 8-character sequence. If anybody is interested in this, I'll explain how that works a little later. But what's of more interest is the efficacy of efficient algorithms. I came across this paper on the internet that looks for the regular expression pattern, n optional a's followed by n a's, and matching it against a string of just n a's. A very simple pattern matching task. What's kind of interesting about this pattern is that if you use a language like Perl or Python to look for this pattern, when n approaches 35, it's going to spend a week looking for that pattern. If n approaches 40, it'll take a year to look for that pattern. But because of the efficient algorithms inside grep and awk, those tasks can be done under a millisecond, even for patterns of length 100. So again, I'm putting in a testimonial to if you implement algorithms, spend a little bit of time trying to make the algorithms efficient because your users will love you for it. Now comes the task of we have an algorithm and we want to translate it into a target program. We want to create a source program that embodies the algorithm and then translate it into a target program that can be executed on a computer. And the device or computer system that does this is known as a compiler. And what a compiler does, I should mention that another area where I really enjoyed my interactions with Jeff was doing compiler research and writing a series of books. Jeff suggested we should put a dragon on the front cover, and these books quickly became known as the Dragon books and were used in compiler courses around the world. I might mention the Japanese translation of our most recent compiler's book has the most fire-breathing dragon I've ever seen in my life. Whoever the artist was that created it, my compliments to them. But these books are even still used today in compilers courses around the world. In the books, we showed that a compiler can be implemented as a sequence of phases where each phase translates a form of the source program into a semantically equivalent form of the source program that's closer to the machine model in the target program. And each one of these phases uses interesting algorithms. The lexical analysis phase, for example, uses some of the fast string matching technology that we had developed. And some of our colleagues used our algorithms to create generators for these phases. So there's a lexical analyzer generator that got to be known as Lex, and a syntax analyzer generator called Yak. I think Jeff invented the name Yak, or at least that's a story that's attributed to him. And these tools, Lex and Yak, are now available with every major programming language that's been created since C. So there's an OCaml version of Lex and Yak, a Haskell version of Lex and Yak, and so on. What these tools do is allow students to be able to generate a compiler for a fairly substantial language in the course of a semester. I'd like to move forward to a very new area that has a lot of interest around the world, both from the research community and from industry, namely that of quantum computing. In the last year or so, more than a dozen companies around the world have announced that they're making major investments into quantum computers. And I'd like to give some background as to why they're doing this, and as an algorithms researcher and a software researcher, talk about the new opportunities that quantum computers bring to the development of algorithms and compilers for quantum computers. So what is quantum computing? You can say it's a study of computational systems that use quantum mechanical phenomena such as superposition and entanglement to perform operations on data. And some of the areas where people have said quantum computers can have significant impact may be in quantum chemistry, looking for catalysts to create fertilizers more cheaply than done today, or being able to create superconducting transmission lines to reduce the cost of energy distribution. All of these require the ability to be able to deal with quantum mechanical phenomena in molecules. However, I should caution that the field is still very much in its infancy, and you shouldn't believe all of the articles that you see in newspapers about how quantum computing is going to revolutionize the world. I'm going to give some words of caution, but also some words of opportunity for research problems that arise in this field. So, being true to my belief that you should first try to come up with a model of computation, let's look at quantum mechanics and see what help it can give us in coming up with a model of computation for quantum computing. And Nielsen and Chung have written the Bible of quantum computing, and in their book they describe quantum mechanics with 4 postulates. And this is the computer scientist's view of these 4 postulates, as opposed to the physicist's view of these 4 postulates, which are equivalent. The first postulate says that the state of an isolated physical system can be modeled by a unit vector in complex Hilbert space. And this gives rise to the notion of a quantum bit. A quantum bit is a 2-dimensional vector in complex Hilbert space. So this slide shows that here's a quantum bit psi, which is alpha times the 0 vector and beta times the 1 vector in this complex Hilbert space. Alpha and beta are complex numbers, and the sum of the absolute values of their squares sum to 1. What alpha represents is if you square its absolute value, you get the probability when you measure the qubit that it will come out with the answer of 0. When you perform a measurement on a quantum mechanical system, the output is a classical bit, a 0 or 1, not a qubit. That's one of the limitations of quantum computing, is that the output is very limited. On the other hand, as I will explain, there are some very powerful parallelism aspects to quantum computing that give it a great deal of potential. The second postulate of quantum computing is that you can model the evolution of a quantum mechanical system by a unitary transform. And a unitary transform is one that, when you compose it with its adjoint, it gives you the identity matrix. What it also says is that quantum mechanics is reversible. Time can run forward and backward in quantum computations. But what this postulate allows us to do is give us the types of operators that we'd like to enshrine in our model of computation for quantum computing, namely unitary transforms. And here is an example of one very useful operator that most quantum computing programming languages have, namely the Hadamard operator. And you can think of the Hadamard operator as the square root of the 2x2 identity matrix. The third postulate of quantum mechanics says, how does a quantum computer get its huge computational potential? And this says that if you bring 2 isolated physical systems together, the state of the combined system will be the tensor product of the states of the component systems. So every time you add a bit to to a quantum computer, you double the size of the state space. So if you have a quantum computer with 300 qubits, the state space is 2 raised to the 300th power. That's more than the number of atoms in the universe. So very quickly, you can create giant state spaces with which you can do computation. And basically, computation in quantum mechanics is just rotating this unit vector in complex Hilbert space according to unitary transforms. And then here I should mention another very useful operator, the controlled NOT gate. It takes 2 qubits as input, and what it does is you have a control qubit that if the control qubit is 0, the target qubit goes through unscathed, and if the control qubit is a 1, then the target qubit gets complemented. And here you can see in this tensor product notation what the input-output mapping of this quantum control NOT gate is. The fourth postulate deals with measurement. I don't expect you to read this, but the takeaways from this is that measurement is not a unitary transform. It's not reversible. It applied to a quantum system collapses part of the state space of the quantum mechanical system onto one of its component basis axes. And the other aspect of measurement is that it's probabilistic. Quantum computing is not a deterministic operation. You get a certain probability of the output. And the way you design quantum algorithms is you want to move that state vector so it's close to the answer that you want it to be. So when you measure it, you get the projection of the vector onto the answer that you'd like. So out of this computational model, we can create our quantum circuit model of computation for quantum computing. And this is the most widely used model for representing quantum algorithms. Quantum circuit has n input lines and n output lines. The computation has to be reversible. You can think of a quantum circuit a little bit like a Boolean circuit, except that the gates are unitary transforms instead of and or not gates. And here's a simple example of a quantum circuit. You apply the Hadamard transform to the top qubit, and then you apply a controlled NOT gate to the output of the Hadamard gate and the second qubit, and what you get as output is what's often called the Bell state or an Einstein-Podolsky-Rosen state. And this output state is an entangled state. This is what cannot be written as in product form, and Einstein used to call these entangled states spooky action at a distance, because if you perform some action on one of the output qubits, the result would be affected by some correlation on the second qubit, no matter how far away the second qubit was, even if it was on the other side of the universe. And, and you could keep the 2 qubits entangled. This is why Einstein thought it was spooky action at a distance. I mentioned earlier that the time complexity of an algorithm is something that we're very interested in the design of algorithms. One of the breakthrough developments in quantum computing was the invention or discovery by Peter Shor of an algorithm for factoring integers. And what he showed was that a quantum computer can factor to an integer in n cubed time, and the best known algorithms on a classical computer are all exponential. And if you're interested in what happens when you replace an exponential number algorithm by a polynomial time algorithm, the results can be breathtaking. What this slide shows is that if you want to, say, factor a 1,000-bit number, you can do it more than 1 billion times faster on a quantum computer, if we could build one, than we can on a classical computer. And the reason quantum computing received such a great deal of attention in the mid-90s was a lot of our electronic commerce assumes that factoring is hard. The RSA algorithm, Ravesh, Shamir, and Edelman, who, by the way, won the 2009 C&C prizes, developed this, what appeared to be a very secure way of encrypting financial data over the internet. But when this result got published, people got concerned that maybe RSA will be compromised, and the NIST, the National Institute of Science and Technology, has recently announced a competition to create a quantum-proof encryption scheme for electronic commerce. So this has already had a significant impact on electronic commerce in the field. Here is a rendition of Shor's algorithm in a high-level language. And the reason I'm showing it is that there's only one quantum step in this algorithm. The rest of the steps are classical computing. And what this illustrates is that we're not going to have standalone quantum computers. They're going to be adjuncts to classical computers, devices like GPUs that you can give a computation to accelerate the computation, but you're going to need the classical computer to prepare the input and absorb the output from the classical computer. So no one is going to run Word or email on a quantum computer. What Shor's great breakthrough was to reduce the factoring problem to order finding, and he then created the quantum circuit to do order finding in polynomial time, whereas the only order finding algorithms that we know of on a classical computer are exponential. Let me just conclude by talking about two other models of quantum computing that are talked about in the literature. There is a computational model called adiabatic quantum computing. What this involves is evolving a Hamiltonian, as in Schrodinger's equation, and letting physics do the computation. You evolve an easy-to-prepare Hamiltonian into a Hamiltonian that has the solutions, and you want the evolution to be kept at the ground state. And the best-known example of a quantum computing device that uses this is the Canadian company's D-Wave Systems quantum annealer. I might point out that the business end of their quantum computer, which is at the bottom of this tower, is kept at 15 thousandths of a degree above absolute zero. This is colder than outer space. So on top of this, you need some dilution refrigerators to chill the niobium rings that store the qubits on those chips. Another model of quantum computation that's receiving a lot of attention these days is called topological quantum computing, and it's being pioneered by the Microsoft Corporation. And this is perhaps the most intriguing computational model that I have encountered. Recently, Horst Stormer and two other people, Horst Stormer was, again, a physicist who worked at Bell Labs, discovered the fractional quantum Hall effect. So if you take a slab of gallium arsenide, chill it, it has to be very pure, put another slab of gallium aluminum arsenide on top of it. In the interface, the electrons form a new state of matter where they evince the fractional quantum Hall effect. And in this electron gas, you can find quasi-particles. And The interesting thing about a quasi-particle, first of all, it's not a particle, it's like a hole in electronics. It's a state of surrounding electrons. So here is an artist's conception of how topological quantum computing works. So here's the interface between these two slabs of gallium arsenide. You have probes, you chill it, and in this vacuum, the quasi-particles emerge. You bring them near the probes. You then put a probe on top of one of them, and then you circle the probe around the other quasi-particles. And the operation of rotating one quasi-particle around another quasi-particle computes a unitary transform. I won't explain why, and I don't think I can explain why. I'd have to know some really deep quantum physics in order to do this. But this is what gives topological quantum computing advantage over more classical models of computation, because the quasi-particle, there are two halves to it, and they're separated. When you do the rotation can jiggle as it goes around the other quasi-particle. So the jiggling doesn't affect what's being computed. It's the completion of the rotation that computes the unitary transform. And then when you're done with the computation, you return the quasi-particles, and what's left gives you the state. And there's a theorem. I got these slides from Steve Simon, who used to work at Bell Labs at the time and who was very interested in braiding quasi-particles as the model of computation. And there's a theorem saying that any computation can be performed by moving a single quasi-particle around others. Let me just briefly touch on compilers for quantum computers. We can use the model of a compiler that Jeff and I talked about in our Dragon books, except at the end we have very different kinds of code generation algorithms and optimizations. And since we don't have quantum computers, you might want to simulate the target program with a classical computer. And I had a PhD student by the name of Christos Faure who was looking at, if we want to do classical quantum computation, say on ion trap machines, there's a lot of interest of, we have to put error correcting and fault tolerant circuitry into the computation because qubits are so fragile. So Ike Chung predicted that an ion trap computer would be 80 or 90% error correcting and fault tolerant circuitry. What we also said at this time was that if we're going to create software for quantum computers, we'd like to have a tool suite, a layered hierarchy of tools with interfaces, say going from programming languages to compilers to optimizers, simulators, and so on, because we want to be able to experiment with the algorithms before we actually try to find a quantum computer to run them on. And fortunately, since we proposed this tool suite, there's a paper in Nature that just came out 2 weeks ago that said basically the same thing. A number of people have created some of these prototype tool suites, and perhaps one of the most advanced is the one that's been developed at Microsoft, where Christos Faure went to work after she graduated from Columbia. And they've developed a language called Liquid, and it's a software architecture and tool suite for quantum computing. It has a programming language that's built on top of F# optimization and scheduling algorithms, and you could actually use it to produce code for quantum devices if we had quantum devices available today. And Microsoft is going to announce next month that a quantum programming tool suite is going to be incorporated into Visual Studio, or at least that's what the president of Microsoft said, and I suspect it's going to be based on Christos' work and Dave Wecker's work, who is a colleague of Christos at Microsoft. So Krista tells me that she can factor a 30-bit integer on her laptop in a month using this tool suite, because they have to deal with vectors of 50 million complex numbers as part of the computation. So they're waiting for the quantum computer to be able to run this. IBM just announced last week that they have a 50-qubit quantum computer available, and you can experiment with some smaller versions of this already. I might mention that my current PhD student is looking at, can we do approximation of combinatorial problems faster and more efficiently on a quantum computer? This is very much of a brand new research area. This idea of quantum approximate optimization algorithms was proposed by Seth Lloyd at MIT just a couple of years ago, and I'm sorry, by Ed Farhi at MIT, and this is being explored as maybe we can, in addition to Shor's algorithm, do approximate optimization, which is difficult. So let me conclude by saying we've gone from Euclid's algorithm to quantum algorithms, but this isn't anywhere near the end of algorithms research. And I think one of the most exciting areas of algorithms is putting algorithms into people. We are already doing this to some degree because we can make prosthetics that interface with the nerves in the arm and have these prosthetics be controlled by the human brain. People are creating cochlear implants. And I was amused by this book written by Yuval Harari saying organisms are algorithms, and how we see the evolution of algorithms in the future is, I think, a space to watch, because they're going to go everywhere. Thank you for your attention.
Thank you, Professor Eho, for your interesting lecture, including the latest analysis of quantum computing.